So the first talk of today is about bootstrapping cosmological correlators from singularities. And our speaker is Austin Joyce from the Delta Institute for Theoretical Physics at the University of Amsterdam. Please.
Okay, great. Thank you so much. Yeah, so let me start by thanking the organizers for setting up this great meeting and for giving me the opportunity to talk. And let me sort of start with sort of a small apology, which is that there really won't be any positive geometry per se in what I'm going to talk about today. But of course, the ideas of positive geometry are very useful in cosmology, and I'm very much of a dilettante, but very excited to learn more about it. And in that regard, this meeting has been very inspiring. And so roughly speaking, the goal of this talk is to give you some idea of what the cosmologists are up to and why, with the hope of maybe fostering more interaction. And let me also just take a moment to acknowledge my great group of collaborators that I've been having a lot of fun thinking about these things with. Okay, so let me really just kind of start at the most basic level, because I realize that many of you are not cosmologists. And so really, it sounds kind of obvious, but cosmology is really a study of correlations. And this sort of explains why the fundamental objects of our interest are going to be correlation functions. And the reason for this is really like we can't generate universes in a lab and do experiments on them. All we get to do is look out in the sky and look at the distribution of stuff that we see. And the sort of remarkable fact about the large scale distribution of things in the universe, like stars and planets and galaxies and clusters, are that they're not randomly scattered about, but they're actually correlated. And so in particular, if you go out and find a galaxy in the sky, you're more likely to find another galaxy a certain separation away from it than others. So there really are some correlations in the way that things are distributed. And what cosmologists do is trace these correlations across cosmic time. And by studying how these correlations evolve, what we do is we infer the dynamics and contents of the universe. So for example, we can trace the correlations seen in galaxies back to the cosmic microwave background, or even back all the way to this, what I'll call reheating surface that is really the hot Big Bang. And just to avoid confusion, when I say the hot Big Bang, I mean like the moment that the universe became thermalized, not necessarily like the initial singularity. And what we do is we infer the statistics of correlations on this reheating surface, which then serve as the initial conditions for the subsequent evolution of the universe. And a remarkable feature of these correlations on the reheating surface is that they're extremely simple. They're well described by a simple power law. But this itself is kind of confusing, because if you really take seriously the statistics of the correlations on this sort of initial time surface, they look acausal in the sense that points which have never been in causal contact are correlated with each other on this surface. And so that sort of requires an explanation, or at least cries out for an explanation. And the inference that we make from this fact is rather simple in retrospect. It's really just that the hot Big Bang is not the beginning of time. It's really that there's some pre-Big Bang phase of the universe's evolution. So the natural question to ask, and sort of the central question in early universe cosmology, is what did the universe look like before the Big Bang? And so the standard answer to this question is that the universe underwent a period of inflationary expansion. And so the resolution of this puzzle that the fluctuations look acausal is answered in sort of the simplest possible way. Basically, we just tack on a bunch of other time evolution. And we don't think of this late time surface as the beginning of time, but instead the future boundary of some pre-Big Bang phase that we call inflation. And during this inflationary epoch, the idea is that the universe looked very close to being de Sitter space, which is like an exponentially expanding space-time. And the future asymptotic boundary of this de Sitter space then serves as the initial conditions for the subsequent evolution of the universe. And the dynamics of this inflationary space-time set up these perturbations that we then infer or see on this reheating surface. And so a sort of remarkable feature of this explanation for the correlations on this surface is that the geometry of the inflationary spacetime ends up being encoded in the statistics of these fluctuations. So already at the simplest level, which is like the correlation between 2 points that we see, for example, in the cosmic microwave background, we infer that these correlations, like I said, are very close to being described by a simple power law. So in the cosmologist terminology, we say they're nearly scale invariant. And what that translates into in terms of a feature of the geometry is that the inflationary geometry is nearly time translation invariant. And so this will be sort of a recurring theme that by studying something about the correlations at late times, you're really inferring something about the geometry that gave rise to these correlations. So something about the time evolution gets encoded at late times. So the simplest correlations, these 2-point correlations, are sufficient to describe all of the data that we see. But they're also not very informative about the detailed microphysics of inflation because they're really fixed by kinematics. And so if we want to probe more in detail what the microphysics is that gave rise to inflation, we want to study higher point correlations, which are really sensitive to the interactions in the theory, sensitive to the way that things are coupled together. And so the microphysics is really encoded in higher point correlations on this late time boundary. And so that's the thing we're going to want to study today. Okay. Aside from this, aside from just telling about the microphysics of inflation, things like particle production and decay in the inflationary spacetime can also be encoded in these late time correlations. And so from a phenomenological point of view, one of the reasons that people are excited about inflation is to use it as sort of a tool for discovery. So the inflationary energy scale is astronomically higher than anything we could hope to produce on Earth. And because there's so much energy in the inflationary background, it can produce real particles that are very, very massive, which can then decay and leave their imprints at late times, which we can then go look for. But in order to sort of realize this hope of using inflation as like a particle collider, sort of in the language of NEMA, we need to have a very detailed characterization of the signals in order to extract them from the data. So the way the searches work are they're really template-based searches. And so in order to find what you're looking for, you need to know what you're looking for. And so part of the motivation for what I'm going to tell you about is really making these types of calculations feasible. Okay, and so one other sort of beautiful feature of inflation is as a consequence of the way that fields propagate, fluctuate, and freeze out in de Sitter space, the time evolution through de Sitter space gets encoded as scale evolution in these late time correlators. So for example, if I imagine that I have some correlation between 4 points on this late time surface, which arose from the production and decay of some particle, by changing the shape of the points on the sky and asking how the strength of fluctuations changes, I'm really making this field propagate different distances in the inflationary spacetime. And so I'm sensitive to different points in the bulk geometry, or sorry, different epochs of time in the bulk geometry. And so there's sort of a very visceral way in that the time evolution in the bulk gets encoded in some object that has no natural notion of time. It gets encoded in the shape or the shape dependence of correlations at late times. And so this combined with another fact, which is that we can't directly image the inflationary epoch, primarily because at the hot Big Bang, the universe became thermal, and it's very difficult to look past this period of thermality. So we sort of just infer that the inflationary epoch was there from the statistics of correlations. So we can't directly image inflation. That combined with the fact that sort of the time dependence of inflation gets encoded in an interesting way in these boundary observables motivates us to ask the question of whether we can just do away with this time evolution picture and construct these observables directly on this future asymptotic boundary. And so the philosophy here is something quite similar to the S-matrix bootstrap, where you try to construct some asymptotic observables directly on the boundary without following the detailed time evolution. So that's sort of the type of thing we're going to try to explore. And so in order to even start to do this, you have to ask the question of, I want a consistent object at the end of the day, but how do I know an object is consistent if you hand it to me? So what are the rules that a consistent cosmological correlator has to obey if it came from time evolution? So I want to talk a little bit about that. But here is probably just a good time to stop and ask if there are any questions about this sort of motivational stuff. Okay, fantastic. All right, so here is just sort of a brief outline of what I want to talk about today. So I'm going to sort of draw a lesson from the study of scattering amplitudes that we should think about the singularities of the objects that we're interested in. So I want to try to start by anchoring these correlators by thinking about their singularities, and then move on to try to extend these correlators away from their singularities, trying to construct them for general kinematics. And I'll try to sort of explain a couple ideas for how to do this. And then I'll finish with some conclusions and outlook. So let me start by just briefly describing what the singularities are of cosmological correlators. And so here, there are many lessons that one could draw from the study of scattering amplitudes. I'm going to choose a particular one. And the particular one I'm going to choose to draw is that much of the physics of scattering amplitudes is controlled by singularities. So of course, you're all very familiar with the notion that if I have a scattering process, at least at tree level, if I have some subset of the momenta add up and go on shell, the scattering amplitude factorizes into some sub-processes with positive residues in simple poles. And in many cases, just demanding these consistent factorization, for example, in theories of massless particles, is enough to completely reconstruct the answer. And so, taking this as some inspiration, I want to just ask kind of a similar question about cosmological correlators. Where can they have singularities, and what additional information, if any, do I need to reconstruct them just from knowing the singularities and their coefficients? Okay. So in order to tell you about the singularities, I first have to tell you what the object I'm going to be interested in is. And the object that I'm going to be interested in is the kind of sillily named wave function of the universe. And the wave function of the universe is just kind of a fancy way of talking about a state at some time. And so importantly, in cosmology, in contrast to flat space physics, there's no time translation invariance. And so the objects that we're interested in are naturally defined on some time slice. And in de Sitter space, that time slice is really the natural one, is the asymptotic future boundary. And we want to talk about correlation functions on this time slice. And so a natural, or a nice way to encode that information is to just talk about the state written in sort of field eigenstates, which is just what this wave functional is. The wave functional you should just think of as a way of writing the state at some time. And in particular, you use this object in the same way that you would use the wave function in quantum mechanics. If I ask you for an equal time correlation function on this surface, and I hand you the wave functional, all you do is square it, multiply by a bunch of fields, and integrate in order to get a correlation function out. And so this is kind of a non-standard way of thinking about QFT, but in cosmology, it's like a extremely natural way of thinking about things. Okay, and the nice feature of the wave function is that it admits a simple perturbative expansion in the same way that correlation functions or S matrix elements do. And so formally, we can write the wave function in sort of some path integral representation. And then in perturbation theory, we can approximate the wave function by its saddle point, thinking of it as the classical action evaluated on, the action evaluated on some classical solution that has the properties that I want. So in particular, some boundary conditions on this late time surface. And again, in perturbation theory, I can expand the wave functional in the following way. It's sort of I'm going to expand it perturbatively in the fluctuations on this late time surface. And appearing in this expansion are some kernels, which tell me how the fluctuations are correlated with each other. And for obvious reasons, I'm going to call these kernels wave function coefficients. And the nice thing about these objects is they can be computed in some Feynman diagram expansion, very similar to scattering amplitudes. And so if I wanted to compute a correlation function, these wave function coefficients contain all the information I need to do that in perturbation theory. And so for that reason, I'm going to totally abuse terminology and just call everything either a correlator or a wave function. You should just identify the two concepts for the purposes of this talk. There are some subtle differences, but they won't be at all important for what I'm going to tell you. But if any confusion arises, feel free to ask. Okay. The other thing I should say is we're also, so here I've written everything in position space, but it's very natural in cosmology to go to Fourier space because things are spatially translationally invariant. And so I will talk about everything in Fourier space. And so I think sort of a nice way to get some intuition or get a handle on what the wave function is about is to just calculate it in some simple examples and just stare at them, because it's not something we learn about in QFT class, although probably we should. But so it's very useful to try a simple toy model and just get some intuition for what's going on. And in this regard, this paper by Nima and Paulo is like super inspiring. They study this very simple model and find a ton of beautiful structure. And so the model that we're going to talk about is just a massless scalar field in flat space with some polynomial interactions. And actually, for the purposes of what I'm going to show you, you can just imagine it's a phi cubed interaction. I'm just going to talk about really very simple things. And what we want to do is to figure out how to compute the wave functional coefficients in perturbation theory. So in Fourier space, basically, we're just going to start drawing Feynman diagrams like we would do to compute a scattering amplitude. But the key difference here is there is some late time surface that we're trying to compute the wave function on. And so now there's two types of lines that can appear in our Feynman diagram. There are lines that connect bulk vertices to each other. And for those, we use something which is very similar to the bulk Feynman propagator, but it has an additional untime ordered piece, which enforces the right boundary conditions, which sort of makes sure we're calculating a wave function rather than a scattering amplitude. And then for lines which go from the bulk to this boundary surface, we use a different propagator. So it's sort of the analog of the bulk to boundary propagator in ADS-CFT, which in this simple model is just a plane wave. So it's some very simple thing. And then for the vertices, we just use, in this simple model, they're just I times a number. I'm going to set this number to 1. And then the other important difference between correlators and scattering amplitudes is that we haven't Fourier transformed with respect to time. And so we have to integrate over all the time insertions of these vertices. And in fact, that ends up being responsible for most of the complication once we go to cosmology. And another important fact is that since cosmology breaks time translation invariance, energy does not need to be conserved. And so these wave function coefficients or correlators will depend on additionally the total energy involved in a process, which doesn't have to add up to 0. Okay, so those are the rules. Let me apply the rules in a couple very simple examples. So the simplest possible example, so if we're thinking about phi cube theory, let's just compute the 3-point wave function coefficient. So it involves 3 of these bulk to boundary propagators. Since they're all exponentials, they all combine together in a nice way. You can do the time integral simply, and you find that the wave function coefficient is just 1 over the total energy involved in this process, where K1, K2, K3 are just the energies of these external lines, if you like. Okay, so that's a nice simple example. The next most complicated example we could do is to just look at the 4-point function coming from exchange. So this is only slightly more complicated. There are now 2 vertices whose time insertions I have to integrate over. And now there's a propagator with some non-trivial causal structure, which leads to some nested time integrals. And just a bit of notation, I'm going to define these k variables with a bunch of subscripts to just be the sum of these energies. So like k12 is like the sum of the energies of these 2 internal lines, and k34 is the sum of these 2 energies. And so you can do these time integrals. It's not so bad. What you find is this slightly more complicated object than this guy. But it has a very simple structure, actually. So you can see naturally there's a piece which looks like the total energy involved in the process. And then it looks like there's a piece that looks like 1 over the energy involved in this left vertex and 1 over the energy involved in this right vertex, where S is the energy of this exchange line. And so the only real lesson that I want you to draw from these extremely simple examples is that these correlators are singular when the energies flowing into a vertex, or more generally, the energies flowing into a subgraph, happen to add up to 0. Okay. And in fact, this lesson is totally general. So here I've just showed you 2 simple examples where it happens to be true, but it is much more general than that. And in fact, those are the only singularities of these correlators. And so let's try to just understand philosophically where these things come from. So first, let's try to understand where this total energy singularity is. So my claim is that a wave function coefficient is singular if the total energy involved in it happens to add up to 0. And one way to understand that is to think about where this divergence would be coming from doing this bulk time integral. And so it's coming from very, very early times, because that's where the limit of integration is going off to infinity. And at very early times, I can kind of think of integrating over the average of all the time coordinates involved in the vertices and then their differences. And the integral involving the average time will take this form, where it'll have a phase proportional to the sum of all the energies of these external legs times this average time. And then there will be other stuff where I integrate over differences. But if I imagine setting the total energy to 0, this integral is totally unsuppressed, and so it will diverge in the far past. And that's really the reason that there's some total energy singularity. And more interestingly is that the coefficient of this singularity is also very simple. And that just comes from the fact that the Feynman rules that I gave you are almost exactly the same Feynman rules that we would use to compute a scattering amplitude, with the difference that we are now integrating over time rather than going to Fourier space or something. But if we had chosen to compute a scattering amplitude in this funny way, what we would do is, instead of integrating over the half space up to this t=0 slice, we would integrate over all of time. And that would give us the energy conserving delta function that we are familiar with. And so then I would get the energy conserving delta function times the scattering amplitude. And since I'm only doing half of that integral, what I find instead is just 1 over the total energy. So it becomes a pole. But nevertheless, the thing that it multiplies when I set the energy equal to 0 is still the scattering amplitude. And so, yeah, so this is one of the reasons I think that correlators are so interesting, is that they're in a precise sense like a one parameter family of deformation of amplitudes, that on the total energy goes to 0 locus, they reduce to scattering amplitudes, or their coefficients are scattering amplitudes, but away from this, they kind of have a different life of their own.
Can I ask you one question?
Yes, please.
You said that almost all correlators have this singularity. And
Yeah.
which ones? They do not have
Good. Yeah.
this one?
So the sort of a famous example that doesn't have this singularity would be something like a Yang-Mills correlator with all helicities the same. So we know that sort of for scattering amplitudes, you have these MHV correlators where at least 2 of the helicities are different. For scattering amplitudes, 2 of the helicities are different. But for correlators, actually, if you set all the helicities to be the same, the correlator is still not 0. But basically, because of some like distributional stuff, this 1 over e is sort of canceling an e in the scattering amplitude. And so the final object doesn't have this 1 over e singularity.
Thanks.
Which I should say is deeply mysterious. So I still don't really understand what this thing's purpose in life is. But yeah, just that's sort of the most notable exception, I would say.
Okay, thanks.
Okay, great. So we can understand the partial energy singularities in almost exactly the same way. So instead of just setting the total energy to 0, we can set the energy of a vertex to 0 and then ask what happens like if I take this left time in the far past. So the same kind of thing happens, that there's some integral over time suppressed by e to the sum of the energies sitting in this vertex. So when it goes to 0, there's a divergence, and I get some 1 over the energy involved in the left vertex pole. And since I know sort of the structure of all the perturbative objects, I can even figure out what the coefficient of this pole should be. And it's relatively simple. I can just stare at the bulk to bulk propagator, take the limit where 1 of the times goes to -infinity. So that kills 1 of the time orderings. And it makes the part of the bulk to bulk propagator associated to this left vertex just look like a bulk to boundary propagator. And then, so this thing kind of looks like a contact diagram where I'm setting the energy associated to it to 0. So I get a factor of the scattering amplitude associated to this left thing coming from that. And then this leftover factor is just the difference of bulk to boundary propagators. And so what I find coming from this right vertex is just kind of a difference of wave function coefficients associated to this right vertex. So the details are not super important, but the important thing is that there's a singularity when this energy adds up to 0, and the coefficient of that singularity can be written in terms of lower point objects. So it can be written in terms of the amplitude associated to this left thing and the wave function associated to this right thing. Okay. And an interesting thing about these partial energy singularities is that they're really a signature of exchange. So correlators that only have the total energy singularity come from some contact-like interactions in the bulk, but things which also have these partial energy singularities, that's really telling you that there's some particle exchange going on. Okay, so kind of another broad theme of the talk is that oftentimes these singularities are extremely constraining. So in the simple examples I've shown you, actually, they're totally nailed by demanding these singularities and these precise coefficients. So this is really unexciting for the 3-point correlator, because the way I've normalized everything, the scattering amplitude is just 1. And I've told you it should have a singularity when k1 plus k2 plus k3 goes to 0. The residue of that singularity better be the amplitude. So it tells me the whole correlator is just 1 over K1 plus K2 plus K3, which indeed is the right answer. But this is actually kind of non-trivial at 4 points. So I can ask, okay, imagine I just know the singularities of the 4-point correlator, but I don't know the true answer. So I can just take the limit of this 4-point correlator when either its left energy or its right energy goes to 0, and it has to factorize in this particular way. And the kind of non-trivial thing is that the left energy goes to 0 limit of the correlator has a residue which has a pole when the right energy goes to 0, and vice versa. The right energy goes to 0 limit of the correlator has a pole when the left energy goes to 0. And so finding something that consistently interpolates between these two limits is now a constrained problem, which I guess in principle, you might not be able to solve. In this case, you can, it's quite easy, but it's kind of interesting in the sense that these funny looking things which have minus signs, you have to interpret as the total energy evaluated at these particular points in kinematic space. And so you infer that, you know, the unique object that has these two limits is precisely the object that we calculated directly, this thing that looks like 1 over E left, E right. And then in this case, the total energy singularity is sort of an output that if I then ask what happens when the total energy adds up to 0, precisely what happens is there's a pole and its coefficient is exactly the flat space Mandelstam S, which would be the right thing for this, the corresponding scattering amplitude. Okay. So before moving on to de Sitter, I just want to make a couple brief comments about this like toy model that I've been talking about. So the first thing is that, so this is sort of the closest approach of this talk with the theme of the conference, which is to say that the wave function coefficients of this simple model that I've been talking about are actually the canonical forms associated with a suitable positive geometry. And I will completely rely on Paolo to explain that to you. And then another important fact is that actually this thing is a little bit more closely related to cosmology than I let on, which is that if I do a very simple thing, which is to let the coupling constants in this theory depend on time, then actually this model can describe scalar fields in some FRW geometries for some values of the scalar field mass. So they're not exactly the ones which are relevant for phenomenology, but they still can capture a lot of features of things in cosmological spacetimes. So just as a totally concrete example, the 4-point function of conformally coupled scalars, which is just a particular special mass, in an FRW space can be written in sort of this integral form where the integrals are coming from making these coefficients time dependent. So in order to capture that at the level of the correlator, you can deform the energies and then integrate over the deformation parameters. And these gamma numbers are really capturing what FRW space we're talking about. And so that's just to say that the thing that I've called the toy model actually gets pretty close to the types of things that we care about in cosmology. Okay, so basically now I want you to just, I'm going to invite you to take a small logical leap with me. So I'm not going to prove to you that all of the correlators have the same singularities in cosmology. Instead, I'm just kind of assert it and give you some plausibility argument for why that's the case. And roughly speaking, the reason that is these simple plane wave factors that were appearing all over the place in the perturbative objects I was talking about before in flat space get promoted to Hankel functions in de Sitter space. And then if I take these Hankel function objects suitably normalized, which I'm going to call F, and I expand them near this conformal time parameter, which is just sort of the cosmological analog of time, if I expand them near the far past, these Hankel functions look like plane waves times some polynomials in, conformal time. And so the fact that the previous expressions diverged when some of these energies adds up to 0 continues to be true, but because of these factors of time, sometimes the precise nature of the singularities is a bit different. But from a physical point of view, what's going on in cosmology is that going to the very far past, because of the physics of de Sitter space, is like going to very, very small scales. And so in the very, very far past, or equivalently at very, very small scales, the physics looks a lot like it lives in Minkowski space. And so we can kind of expect that the singularities we identified in Minkowski space will continue to be there in cosmology. Okay, so this is just some kind of plausibility argument, but you can make everything a lot more robust. But in the following, I'll sort of just assert that this is the case and then see where it takes us. So I'm going to take the locations of the singularities and in fact their residues as an input. Okay, so maybe here is a good place to stop and ask if there are any questions again.
Sorry, Austin, can I ask something about these local singularities? Not when you set the total energy to 0, but you send some part of the energy, so energy around the vertex to 0. So am I correct? Is it correct to think about this as some sort of soft and or collinear limit in the language of scattering amplitudes?
Yeah, good question. So something I haven't quite told you yet, but which is important, is that these singularities can't actually be accessed for physical configuration. So in order to get to them, I need to analytically continue some of the energies. And so I mean, if I allow myself the freedom to analytically continue the energies, I can reach them at sort of general kinematics. So it doesn't necessarily correspond to some collinear limit or something like that. But it will actually be important that these things can't be accessed for physical configurations.
Okay.
Does that make sense?
Thanks. Yeah.
Yeah, and sort of philosophically, so the generalization of this, so I've only told you at 4 points because I'm only going to really need 4-point stuff for most of the talk. But the generalization, if I had a more complicated graph, would be if I have some, the energy in some subgraph adding up to 0, there's a singularity. And you can kind of think intuitively what's going on is like if I take all the vertex insertions of that subgraph and evaluate them all at very early times, they sort of behave like they're in flat space. And so I get something that looks like a scattering amplitude associated to them. That's sort of the intuition. But thank you for the question. Any other questions?
I have one.
Yes.
So here you are taking singularities as an input, right?
Mm-hmm.
Are there, maybe you will talk about this. Are there other inputs that you can also take to fix?
Yeah. So I will talk about this a little bit. I mean, I guess it'll be a bit related to the things I'm going to talk about, that there are various ingredients, and I guess you're allowed to take any of them as being the most fundamental possible thing. Maybe the sort of most natural alternative way to proceed would be to take as fundamental the symmetries of de Sitter space and say, I know that these final objects have to be compatible with the symmetries of de Sitter space. And so I'm just going to ask what are the most general things compatible with symmetries. And then I'll find that, so this implies a set of differential equations, like I'll show you in a minute. And then I can just like find out that some of the solutions of these differential equations have various singularities. And then I have to sort of infer which singularities correspond to what types of bulk physics. So here I want to sort of take the, sort of advocating the approach that I want to like start by doing things at like tree level in the bulk and stuff like that. And so I want to use as input the singularities that I know tree level stuff has and try to leverage that to figure out what the correlators are. But of course, you could proceed in a different way where you kind of learn that the final objects have these singularities at tree level. Yeah, I think, to me, this is sort of a conceptually appealing way to proceed, but of course you could have a different starting point.
Thanks.
Okay.
Can I ask a question before? I'm not sure if this is the right time for the question. If it isn't, tell me and I'll ask it again later. But you said early on that you're talking about the wave function, and then there's just some extra step to mod squared and get the answer. This is something that I think is also very annoying, at least to me, in thinking about amplitudes, that we go on and on and all these amazing properties of amplitude, blah, 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 blah. But at the very end of the day, we mod squared because Born told us to do it, in 1927 or whenever it was. And it's not clear why we're mod squaring it. Is there anything sort of new that happens for the actual correlation function? Is there a sort of is there a qualitative difference, anything that has struck you? For here in cosmology, where it's even more vivid because we're literally taking a wave function and mod squaring it. Is there something sort of better about mod squaring, noticeably different about the structure of the singularities?
Yeah, that's a great question. So I don't think there's anything noticeably different about the structure of singularities in particular.
Do
And I
things
think,
cancel, add up in some interesting way? Anyway, you know what I'm saying.
Yeah. No, I mean, to be honest, I don't know. I mean, for the most part, like, I only know really what's going on at like 4 points, where, as you know, there's not like a huge difference between the squared object and the unsquared object. So I think it could be true that at higher points, something very interesting happens. And I think that's sort of something we probably have to grapple with at some point. So I sort of very flippantly said, okay, these things have the same information. But of course, as you know, it's like an extremely non-trivial reshuffling of the information. And figuring out exactly how that happens, I think, is probably something we have to grapple with. But I don't know yet. No.
It would just be really cool if there was some damn reason internal to this way of thinking why we have to mod square.
Yeah.
Until we figure that out, there's something really missing in this worldview. I think in this general worldview, both for amplitudes as well as the correlators. Yeah.
Okay. Thanks. No, that's totally fair. Yeah, and I think, I mean, yeah, this question is also sort of related to, like, if you want to have some holographic description of cosmology, like at 0th order, I don't even know if there should be a holographic thing, which is computing the wave function or computing directly the correlators.
Yeah, absolutely.
And so, absolutely. I mean, I feel like if one of them was way more special than the other, then you'd know. You'd say, okay, you know, this one's much better. But
that's why I was asking the question at this much more baby level, just to see whether we see any hint for the mod square. But anyway.
Yeah. Honestly, I don't know. It's a great question though. Okay, cool. Yeah. So so here I've sort of like told you where the singularities are. So just as like a super recap, I'm only really going to talk about the 4-point function, and the 4-point function can be singular in 3 limits. It can either be singular when the total energy adds up to 0, where the coefficient of the singularity is the 4-point scattering amplitude, or it can be singular when one of these partial energies add up to 0. And these coefficients are just some lower point objects like amplitudes and lower point correlators. But importantly, as I mentioned, these singularities lie at unphysical configurations. In particular, I'm forced to analytically continue some of the energies in order to access these singularities. And so I can't directly probe them by any physical real process. But nevertheless, we're extremely familiar with situations, for example, in complex analysis, where knowing where the singularities are in the complex plane controls the structure of a function, like on the real line or something. And so the goal, roughly speaking, is to try to figure out whether we can leverage knowing things about this function in unphysical configurations in order to figure out what's going on for physical configurations. Okay, and so there's a small complication in de Sitter space compared to flat space in trying to do this type of thing, which is that in the flat space examples that I showed you, everything is extremely simple. All the singularities were simple poles. It was life was great. But in de Sitter space, since I'm now doing integrals over like products of Hankel functions, it quickly becomes very, very bad. And the singularity structure of correlators is oftentimes much more complex than their flat space counterparts. And so here are just like 2 examples to illustrate the point. So one, this is the 4-point correlator coming from exchanging it's just the 4-point correlator of conformally coupled scalars. And you see already at tree level, this thing has branch cut singularities. As another example, this is the 4-point function of some derivatively coupled scalar field model. And you see, not only does this thing have some simple poles at various locations, but it has a whole string of subleading poles in these various energy variables. And so we need to figure out, the thing that I told you is really a statement about the leading singularity. And so we need to put in some additional information about these subleading singularities. And then there's sort of a further conceptual complication, which is that these various energies going to 0 are not de Sitter invariant conditions on the energies. And so the locations in kinematic space where things are singular don't necessarily have the full symmetries of de Sitter space. And so trying to extend the object away from these singularities in a way which is de Sitter invariant is a non-trivial goal. But roughly speaking, that is the goal. We want to find a way to reconstruct the correlator at general kinematics using these singularities as an input. And so I want to just kind of give you a flavor of 2 different strategies for doing this kind of thing. One, so remember, we want to understand how the shape of correlation or the strength of correlations changes as we sort of change the energies and momenta involved in the correlator. So since we're in Fourier space, the correlator is really a function of 4 momenta that have to close to form a quadrilateral. And we can ask what happens as I change the shape of this quadrilateral. So in particular, as I deform away from one of these singular locations, and we can try to just find a differential equation that tells us how the strength of correlation changes as we change the shape. Or alternatively, in many cases, we'll see that the correlators of interest in cosmology are actually rational functions. And so demanding that they factorize correctly on their singularities, and that also some sort of weak information about bulk unitarity will often be enough to completely fix them. All right, so let me first start by talking about differential equations. And here is sort of, you know, I could have told the talk in a different way and just said this was the fundamental input. But yeah, sort of the philosophy I'm advocating is slightly different. But the idea is that we know.
Sorry, can I just ask you? I'm just a bit confused. You can put different inputs together also. I don't understand. So you say I could have started from this input, but can I put the different inputs together? In principle? Maybe it's not a relevant question. I don't know. I mean, add all the information that I want to get.
Yeah. I mean, if you like, these are these two things are sort of two slightly different inputs.
But I can add them.
Yeah. You can of course combine them.
In the sense, combine. Yeah. Okay. Thanks.
I think one of the things that Austin was saying earlier is that there is more overlap between them than you might naively think. Like for amplitudes, the analogy would be, we say the amplitudes are Lorentz invariant, statement 1, and statement 2, we ask for them to have certain kinds of poles and factorization and so on. And they're really separate things. Here, they're slightly more, they can be slightly more intertwined, because as you start looking at the solutions of the differential equations, as you'll say, at least a particular sort of solution to the differential equations have singularities anyway. And so there's more overlap between them. And I think that's why, am I understanding that that's what you were saying earlier?
Yeah.
Correctly?
Okay. Yeah, that's what I meant. Yes.
Yeah. But of course, you can talk about them both together, but they're more, they overlap a little more here than they do in amplitude.
Okay, thanks.
Okay, great. Yeah. So I want to just so we can think about things the following way, which is that I'm claiming there's some phase of de Sitter expansion, which gives rise to these late time correlators that I'm interested in. And so the final correlation functions that I get have to be compatible with the symmetries of this space-time. And so I can just ask, what are the constraints that the symmetries of the space-time place on the correlation functions? And so this is just a reminder of what the de Sitter space looks like, although it won't be super important for what I'm going to show you. The important thing is that the isometries of de Sitter space actually leave a particular time slice invariant. It just kind of mixes around points on this time slice. And in fact, the de Sitter symmetries act exactly like the conformal group on this late time boundary, which is great because this late time boundary is exactly what we're interested in. And so if I ask more in detail what the consequences of the de Sitter symmetries are for this late time boundary, it turns out that what they imply is that the wave function coefficients have the same kinematic properties as correlation functions in a CFT, which would live on this time slice. And so here, importantly, I'm not using any information about like a detailed DS-CFT correspondence or anything like that. What I'm making is just a kinematic statement that there's some set of differential equations that late time correlators have to obey as a consequence of their symmetries. And that's just like a purely kinematic statement. And these happen to be the same differential equations as correlators in a CFT. Okay, so it turns out that for 2- and 3-point functions, things are completely fixed by kinematics. And so they don't really contain any information about the dynamics, though it's still interesting that they're fixed by de Sitter symmetry. The first place where dynamics really enters is at 4 points, where we can get different 4-point functions depending upon the details of the theory. And so the natural way to proceed is try to solve these kinematic word identities that come from de Sitter symmetry, subject to some constraints on what types of singularities that they have. So the simplest thing to do is to solve these differential equations and ask for the answers to only have total energy singularities. And it turns out that these solutions correspond to like contact-like interactions in the bulk. And so the first like really non-trivial thing that happens is if I ask, how do I find a solution that corresponds to an exchange of some massive particle in the bulk de Sitter space? And so what I'm going to do is to try to explain to you sort of how this differential equation looks. So you can translate the consequences of de Sitter symmetry into a differential equation that this 4-point object has to obey, where I've made some assumption about its singularities, demanding that it only has the types of singularities appropriate for exchange. And at the end, what you find is some differential equation of the following type, where there's some differential operator whose details are not particularly important, but it's sort of a hypergeometric type. And so this f is really some generalized 2-variable hypergeometric function, but it's not super important. But the important thing is the differential equation is of the following schematic form, that there's some differential operator that when it acts on this 4-point correlator, what it does is it kills all the exchange singularities and generates one of these objects that has only contact singularities. And so then given some, I imagine these things are completely classified. I just choose one to use as the source. I can then solve for this exchange correlator. And the intuition is that this source is really telling me like what the precise details of the 3-point vertices giving rise to this correlator. Okay, and so sort of an interesting fact already, the mere existence of this differential equation is already kind of interesting because we didn't put directly in any information about bulk time evolution. We really just said, okay, there's some symmetries, I have some singularities of the correlator, I'm going to demand that they're compatible, and I find a differential equation the correlator has to satisfy. And philosophically, this differential equation is saying, you know, there's some operator that I act on the 4-point correlator and it turns it into a contact correlator. So it, you know, collapses this internal line. And what you can think of this as the boundary manifestation of the fact that there's like some bulk Green's function connecting these vertices. And so this differential equation really is literally this bulk Green's function differential equation translated to the boundary. And so this mere fact that there's like some operator that kills the exchange singularities is already telling you something about locality. It's telling you that the exchange in the bulk was local. So that's already kind of interesting. And so then given this differential equation, it's straightforward to solve it. So it's second order, I need 2 boundary conditions. So here is where I'm going to like explicitly put in the information about the singularities. So this f, when one of its partial energies goes to 0, has to factorize in the appropriate way, where I demand that I know what the factorization limit looks like, and this sort of normalizes the solution appropriately. And then the second boundary condition that I'm going to use is sort of using singularities, but in a slightly different way. I'm going to demand that the singularities I told you about are the only possible singularities of this function f. So a generic solution to the differential equation will have a singularity in this kind of funny configuration where the quadrilateral degenerates into a triangle, sort of in this folded configuration. And so the other boundary condition we're going to use is to just demand that's not there. And so this is related to the fact that in de Sitter space, there's like a infinite number of de Sitter invariant vacua, and we have to like make a choice. And so demanding the singularity is not there is effectively the same as making a choice of de Sitter invariant vacuum, which ends up being the one that people typically choose. So it's kind of nice that the most preferred de Sitter vacuum is actually also preferred from the viewpoint of singularities.
Austin, one question.
Yes.
This requirement of absence of folded singularity, is it true just for scalars or it is completely general for any states?
For external states, you mean, or internal states?
Anything, both internal and external.
Yeah, so I think if you have like massive, higher spins or something on the internal state, it's still true.
For example, if you are considering Yang-Mills.
Oh yeah, if you're extending Yang-Mills, for sure, it doesn't have these folded singularities. Yeah, as I hopefully I will have time to say, I think. So you can like solve these differential equations to get Yang-Mills correlators, but it's like very messy. But you can also get them either by this like weight shifting approach or by some other things that hopefully I'll be able to tell you a little bit about.
Yeah.
But yet, at the end, the final things never have these folded singularities. Yeah.
Okay. Okay. Yeah. Thanks.
No problem. Okay. Yeah. So once we know the solution to the differential equation. Here's kind of like a neat feature of it. And it's sort of a very vivid manifestation of the unphysical singularities controlling the physical object. So it turns out that for this massive particle exchange, already at tree level, the tree level correlator has a branch cut. And this branch cut goes all the way from this partial energy equals 0 locus to the boundary with the physical region. So first of all, it's interesting because we're already seeing branch cuts at tree level, which the interpretation is really that the bulk de Sitter physics can produce particles. But the interesting thing is that now that this branch cut goes all the way to the edge of the physical region, you can imagine trying to probe it by approaching this branch cut from the physical region. And what happens is that the presence of this singularity enforces that the strength of correlations oscillates as you approach this boundary of the physical region. And again, this is another manifestation of the physics of time getting encoded in a non-trivial way in this static object, because what's going on is that as you change the shape of this correlator in order to approach this boundary, we're really kind of collapsing the correlator, making its diagonal really, really short. And as we change the length of this diagonal, we're really probing different epochs, or we're making the exchange particle propagate different distances in the bulk de Sitter spacetime. And this oscillation is really just the oscillatory phase that this massive particle has as it propagates. And so if you're interested in phenomenology, this is like very interesting, because if you could measure this correlator, you could extract the mass of this particle from this ring. Okay, so the thing I told you so far is about a very simple restricted 4-point exchange correlator. So I'm really just talking about the 4-point correlator that arises from the production or exchange of a massive particle between very special external states. And this thing was obtained by solving some differential equations, which are a consequence of de Sitter symmetry. But you might be interested in more complicated situations. You might be interested in situations where the particle exchanged has spin, or whether the external particles have spin, or things like that. And it turns out that because of the connection to conformal symmetry and conformal field theory, we can actually leverage the connection to CFT to utilize some technology which was developed to study conformal field theories to study cosmology. So it turns out that in the context of CFT, a set of differential operators that effectively change the quantum numbers of CFT operators was developed, these so-called weight shifting operators. And for our purposes, the thing that these weight shifting operators do is, given a set of differential equations which come from de Sitter symmetry, I want to find their solutions for various quantum numbers for the field, so various masses and spins. And what these weight shifting operators let me do is, given a particular solution to some one of these kinematic differential equations, I can act with these weight shifting operators to generate a solution to a different differential equation with a different mass or spin of the various particles involved. And so in particular, given this scalar exchange correlator, there's a very simple way to generate the exchanges of higher spins and stuff like that by just acting repeatedly with some differential operator. And this is kind of nice. This is already like a first hint of some simplification from the boundary point of view, because if you were to try to do these individual calculations in the bulk, you would have no inkling that they were related to each other in such a simple way. But you can see from the boundary that there's sort of some universal structure, which is just the scalar correlator that's capturing something about the exchange, which then you can dress with the right kinematic information using these weight shifting operators to generate more complicated processes. And so from the perspective of phenomenology, this is like an extremely useful thing to be able to do. But maybe a more like conceptually useful thing to do is that we're often interested in correlation functions involving massless spinning particles, because they have more constraints on top of the constraints of, in flat space, massless particles are constrained more than just being Lorentz invariant. They have to be gauge invariant and stuff like that. And so here, we might also be interested in asking, what are these slightly more rigid objects like in de Sitter space? And using these weight shifting operators, you can just easily change the external spin of correlators, which is kind of useful, because if I were to try to solve the analog of the differential equation I showed you for the scalar case, it's a gigantic mess. And so it's much, much easier to just generate the solution in this kind of algorithmic way. And much like flat space scattering is highly constrained involving massless particles, an important feature of massless correlators is that in addition to these kinematic constraints that I explained to you, they have to also satisfy these like current conservation word identities, which is basically just the statement that if I have a correlator involving a massless spinning particle, its longitudinal part is not completely free, but it's fixed in terms of some lower point functions. And so the challenge of computing correlators involving massless spinning particles is a little bit more non-trivial. I have to find something that both has the right kinematic properties and solves these current conservation word identities, and I have to solve them both at the same time, which can't always be done. So there's some menu of consistent theories that solve both of these things at the same time, much in the same way that there's a menu of consistent interacting theories in flat space. Okay, so let me just give you the simplest possible example of this, which is like Compton scattering. So this is just, imagine the correlator associated to having two massless spin 1 particles and two scalars. And I'll take the scalars to be conformally coupled. So actually this example is the same in flat space and in de Sitter space. And using this weight shifting approach, you can derive various kinematic objects that have the right properties, but then they get connected together by demanding that they also satisfy this current conservation word identity. And kind of interestingly, there are various pieces, each of which you could associate to like a bulk Feynman diagram, but which then get linked together by this current conservation word identity. So this is like some S channel exchange, and this is like some T channel exchange, and you have to have both of them in order for everything to be consistent. And just a quick note about these spinor variables. So in cosmology, there is a preferred time direction. And so you can, there's a bracket connecting together the lambdas and lambda tildes, if you like. So there's really only one type of spinor in cosmology. Okay, yeah, so this like fact that there's some rigid structure that, you know, these individual terms are not consistent on their own, and the generalizations to involve other interactions are really some boundary manifestation of things like bulk charge conservation. A slightly dissatisfying feature of this object is that it's totally irreducible in that only this object is consistent, like when you add all these terms together. But as I just showed you, it still comes disassembled into something that looks like a Feynman diagram. And so it would be nice to find some way of writing this which like doesn't look like a decomposition into channels at all. And just as a comment, I won't show you details, but you can extend this type of thing to more complicated cases involving gravitons and stuff like that.
Austin, can I ask a question?
Yeah.
If you take the flat space limit for each term, presumably it corresponds to Feynman diagrams in some non-Lorentz invariant gauge or something like that, or some right? Because so what is it? But it's not light cone gauge. Is it like Coulomb gauge or something? Do you know?
Yeah, that's a good question. Let's see. My guess would be it's axial gauge, because that's sort of the gauge which is most compatible with the boundary.
All right. So close. So okay, right. I see. But okay. Yeah,
that's right.
That makes sense.
Yeah.
All right.
But there is a very non-trivial thing, which is that each of these individual terms are not Lorentz invariants, but of course, when you combine them all together, there's like a bunch of spinor magic that they do combine into something Lorentz invariant. Right.
No, I was just trying to understand whether, I mean, one reason this decomposition might be a little more natural in cosmology is just that since there's a preferred time direction, I mean, we know the actual amplitude cannot be broken up into the sum over channels without breaking Lorentz invariance. But here, the fact that we have a preferred time direction is giving you at least a natural way of decomposing it. I was just wondering which natural way, but you're saying it's probably axial gauge, which sounds right. Yeah.
I think so. I'm not 100% sure, but I think that's right. Yeah, I can check though.
Sure.
Okay.
Thanks.
No problem. Okay, yeah, maybe I should ask if there are any other questions, and then I'm cognizant of the fact that I have like 2 minutes, so I'll try to wrap up. Are there any other questions at this point? Okay, great. Yeah, so here, so far I told you like using differential equations to try to extend these correlators away from their singularities, but yeah, maybe I'll just try to give you a flavor for the types of things we were thinking about in this recent paper that came out like last week, where we're trying to take advantage of the fact that correlation functions that we care about in cosmology oftentimes are simpler than the generic case. So I showed you this case where you have a massive exchange, has branch cuts and all sorts of crazy stuff happening at tree level. But for things like gravitons or the inflaton, which are massless particles, typically the final correlators are rational functions. So they have sort of a simpler than generic singularity structure. And so it stands to reason that, maybe we can get away with a little bit less input of, bulk locality. Maybe I don't need this full differential equation. Maybe I just need some slightly looser constraints, which will end up fixing the structure of these rational objects. So I can't just, it's still not the Wild West. There are still constraints because, these correlators have subleading singularities that I have to get right. And so I do need some additional input beyond just the leading singularities. But the claim is that I don't need this full differential equation. And roughly speaking, the idea is to derive the analog of some Kutkowski-like identities, which then, the consistency constraint will be that the correlators have to have the right cuts, which then will fix these subleading singularities. And I should mention there's been a lot of other recent work, particularly by Enrico Pyer's group at Cambridge, sort of exploring similar ideas. And in particular, this paper exploring the constraints of bulk unitarity was very inspiring. Okay, so instead of using this box greens function equals a delta function piece of information, I'm going to use a sort of weaker version of locality in the bulk, which is to just notice that if I take the bulk to bulk greens function and I add to it its complex conjugate, all the theta functions cancel out. And instead, I just get some object that is completely untime ordered. And so the bulk-to-bulk propagator plus its conjugate sort of splits the internal line into two separate integrations that I can do. And this, roughly speaking, is the wave function version of this famous distributional identity that we use in flat space in cutting. Okay, and then I want to use some information from unitarity as well. Roughly speaking, because I want an excuse to construct objects where G plus G star appear in combination. So I can use this identity to get rid of the time ordering. So in order to do that, I'm going to define kind of what will seem like a slightly funny object, but it will become more natural in a moment, which is to define this conjugate wave function, where I'm going to compute it using all the same rules that I used for the regular wave function, except bulk to bulk lines, I'm going to use the complex conjugate of the bulk to bulk propagator. And for vertices, I'm going to use minus I times the vertex factor instead of I times the vertex factor. And the motivation for defining this object is that it's not exactly the complex conjugate of psi, but in a unitary theory, it's very simply related to the complex conjugate of psi. So roughly speaking, let's work for simplicity in the situation where V is just a number. So there in perturbation theory, unitarity tells me V is just purely real. And so it's clear when I complex conjugate this, I'm getting back just the ordinary wave function up to the fact that this thing is now complex conjugated. So I have to flip the external energies in order to get back to the right bulk to boundary propagator. Okay, so this relation is true in a unitary theory. And the reason to use K here instead of K star is I want to be able to add things up and strip off all these bulk to boundary lines and just think about the bulk to bulk propagators and combine them together in nice ways. Okay, so now I just want to put these two things together. So imagine taking psi and adding psi bar to it. So here I have the bulk to bulk propagator and the anti-bulk to bulk propagator, if you like. And they're appearing in exactly the right combination that I can replace them with this untime ordered object. And that has the interpretation of snipping this external line. And so then I can just calculate this thing directly in terms of lower point functions. It just looks like a suitable product of lower point stuff. And I can give this kind of a nicer graphical interpretation by flipping some of the energies. And I'm just going to snip off the external lines just to make everything look nicer. And the right graphical interpretation is I imagine taking this two-site graph corresponding to a single exchange. And I move through it and consider all possible partitions of this thing into a right side and a left side, where on the right side, I flip the energies involved in the vertices, the external vertices. And on the left side, I don't do anything. And then if I happen to cut an internal line, I use this, I shift the two wave functions associated to these vertices. Okay, and then the claim is that once I choose a rightmost vertex, I just move through a graph and do this and partition it in all consistent ways. And then the sum of all of these cuts add up to 0. And so here, these two kind of trivial cuts correspond to psi and psi star here. And then the non-trivial cut is like this shifted wave function. And this gives a non-trivial identity that the wave functional coefficients have to satisfy. Let me not dwell on this too much, just to say this can be generalized to sort of an arbitrary graph. And maybe kind of a non-trivial thing is that depending upon what vertex I choose to be the rightmost, I get different looking identities. So like graphically, for the 3-site graph, both of these identities are true. And so, yeah, it sort of suggests that maybe there's like some invariant notion of cutting, but maybe a question for you all is whether this is like a natural operation at the level of the cosmological polytope, and yeah, maybe whether there's some connection to this like idea of Steinman rules. Yeah, okay, so let me kind of skip this because I'm a little bit over time. But the idea is just, okay, this is now an additional constraint on the singularity structure, and so we can use it to constrain something about the subleading singularities. But let me not go into the details. And then sort of a related idea is that similar to how I showed that FRW correlators can be written as sort of integrals of these flat space wave function coefficients. In other cases involving spin, you can write correlators as sort of operations acting on flat space objects, which I'm happy to talk about. So let me just kind of briefly conclude. So I think that, you know, there's sort of a beautiful thing about correlators, and one of the reasons that I'm interested in them is that they're in a precise sense a deformation of a scattering amplitude, and they contain scattering amplitudes within them at some particular point. And so it would seem crazy to me that there's all this beautiful structure at the scattering amplitude point, which then just disappears when you move away from it. So it seems like there must be analogs of all these beautiful structures found in scattering amplitudes in the last, I don't know, 30, 40 years. And I think we're just starting to like see hints of this in cosmology, but you know, it's still, I don't know, we're maybe at the point that the study of scattering amplitudes was in the 60s or something like that, you know, so there's still a long way to go. And I hope that I've convinced you that many of the features sort of follow from singularities, and that you can translate the challenge of bulk time evolution into the challenge of extending away from these singular limits. And so there's sort of a reorganization of thinking about the physics of time into thinking about the physics of these correlations as a function of shape on the future boundary. And so if you're interested in something like holography, this seems like sort of a, you know, interesting way to go about understanding the emergence of time. And I didn't talk about it very much, but if you care about things like phenomenology, actually explicitly computing things, these tools are actually pretty useful. And then maybe just to end on a kind of philosophical note, to maybe inspire discussion, I think it's fair to say that we sort of haven't found like the Park-Taylor formula for correlators, in the sense that I don't think we found an object that's like way simpler than it has any right to be. And as I mentioned before, it seems like the main difficulty is that things come disassembled into channels. And so it's hard to see, you know, what the right way of writing these irreducible objects is. I kind of suspect there's probably some way of writing it that doesn't look anything like Feynman diagrams, but I don't know exactly what that is. And just a simple example to illustrate that maybe this is not a fool's errand. Here's 2 ways of writing the flat space correlator for a single massless spin 1 and 3 scalars. So this is the thing that would naturally come out of a Feynman diagram expansion, where it has the property that its partial energy singularities come from these individual terms, which makes sense because it came from Feynman diagrams. But there's a conspiracy between these 2 terms in order to get the total energy singularity right. But there's a completely equivalent way of writing this, where you do a bunch of spinor algebra, where you can now localize the total energy singularity into this piece. So only this piece contributes to the scattering amplitude pole. But then there's a conspiracy between the various terms to get the partial energy singularities right. And so this thing wouldn't naturally come from a Feynman diagram. And to be honest, I don't know how you would get this type of formula directly. And I've totally failed to find analogous formulas for more complicated processes. So maybe they don't exist, but somehow I suspect they should exist. And maybe one way to think about getting these types of formulas is to understand whether there's a positive geometry underlying spinning correlators where these various pieces would have to combine into some bigger structure. So I'll stop there, and I'm happy to talk more and answer questions.
Thank you, Austin, for this great talk. Are there questions?
Can I ask, in your cutting formula,
Yeah.
is there a derivation of this formula that parallels the largest time equation for amplitudes?
Yeah, not quite. So yeah, it's a very good question. The problem is, roughly speaking, that there's this non-time ordered piece that really messes you up.
Right. Yeah, I guess so.
So yeah, I don't know. I mean, the way I know sort of how to derive this is some. Well, yeah, okay. So one thing to say first of all is these things are actually all true at the level of the integrand. They're really just statements about like sums of bulk-to-bulk propagators.
Right.
And
but
the only way I really know
the largest time equation is something that manifests at the level of the integrand too.
Yeah,
so.
yeah, totally. So in that sense, they're similar, but the only way I know how to really prove this is like some kind of iterative way that like you assume it's true for some graph, and then you think about adding a bulk-to-bulk propagator and see that it's still true. But yeah, so originally I tried to prove this in the same way as the largest time equation and like totally failed because of these non-time ordered pieces.
Yeah,
but,
I mean, my feeling about the case of the largest time equation is that really is something which is conceptually simplified by thinking about the scattering facet of the cosmological polytope. So it would be very disappointing if the cosmological polytope doesn't have something to say about this extended equation. But
yeah, I mean, somehow, like, I don't know, maybe I just have like too much affection for this kind of thing, but I think it's kind of funny that there are these like different identities that are all philosophically similar, and it feels like something kind of invariant, but I don't quite know what it is.
Right. And can I ask just back to your final point? I mean, even when we don't have spin, when we don't have spin, we still have well, we don't have a sum over channels, I guess. Maybe that's what you're saying. So already each one of these terms in the diagrammatic expansion, you're summing over all the orderings and all that stuff, all the time orderings and stuff already into that sort of into the composite object. So for each one of those two terms, like each one of those two terms is really secretly the sum of a bunch of other terms. But anyway, you've summed them all already. So can you say what's exactly wrong with each term? So they don't have the correct total energy singularity. Are they just wrong for all the singularities? Are the residues wrong for all the singularities? Or well, maybe I can say it another way. What's good about each term? Is there something good about each term by itself?
Yeah, totally. So in this way of writing it, the thing that's good about this term is that it has exactly the right like left partial energy singularity in the S channel and the right partial energy singularity in the S channel, which is not surprising because it's like an S channel object.
I see.
And this thing doesn't contribute to either of those singularities. So this guy gets those things right by itself. And similarly for the T channel for this guy.
I see.
But then the two things have to combine to get the total energy singularity right. And similarly, only the two terms together satisfy this current conservation ward identity.
Right.
And then this is like a different way of writing it where this guy by itself gets the total energy singularity right. And then actually these guys by themselves get these right partial energy singularities right. But the left partial energy singularities require conspiracies between these two terms. So it's sort of
I guess maybe even just at 4 points, maybe the most invariant way of asking my question, which I think you've alluded to a few times, is which one? I mean, we have these two kinds of singularities: total energy and left and right. And who's the boss? Is it true that if I just force an object to have the right E total singularity, like you do in the bottom line, is the sort of reparation needed to make the partial E left and E right singularities? Is that kind of forced on me?
Yeah, not as far as I can tell, actually. And part of the reason for that is it's a little tricky actually to force something to have the right total energy singularity because there are various different ways of writing the scattering amplitude away from E equals 0.
Right.
And so depending upon the details of how exactly I choose to do that, these terms will look different. And so Yeah,
that's I guess what I was asking. I mean, even allowing yourself that freedom, could you write? Is there a second formula that you could? Well, I guess not. I mean, I guess there is not a second formula that has the correct singularities on E total, E left, and E right. This is the unique object that has all those singularities. But okay, but I see what you're saying. So you're saying that it's a little bootless comment, because whether or not you can uniquely fix the rest of the terms depends on how you precisely continue away from E total equals 0 for the
yeah, exactly. And so for example, the next most complicated case would be like Compton scattering or something. And there, I don't even know a formula kind of conceptually like this, because the analog of this scattering thing can take many different forms, and that shuffles all these things around. So here there seems to be sort of a right way of writing the scattering amplitude, but that seems kind of special to this case. So yeah, I don't know. I mean, it's very speculative. I'm not sure exactly what's going on.
I mean, maybe one of the problems is that the conformal invariance equation, or the word identity, however you want to say it, is some differential operator acting on this guy, right? So it's hard to see from just staring at the expression, just algebraically, that it satisfies that property. Because that's I guess what's wrong individually with each one of these terms. And the top line is that they don't satisfy that word identity slash.
That's right.
Right.
That's right.
But that's something that's hard to just see. I mean, it's not an algebraic matter of staring at them. You have to see that this differential equation is satisfied. Right.
That's right. But in this particular case, that statement is actually equivalent to the statement that they individually have the wrong total energy pole.
I see. Right.
But in more complicated situations, it's a little different. Yeah, maybe, I mean, I think there's a similar question that one could ask that doesn't involve necessarily spinning particles, which is like, I don't know, for something like Yang-Mills, there should be some conspiracy between exchanges and contact terms so that they have the right soft limits and stuff like that. And there should similarly be some way of bundling them into something irreducible, right?